Hello friends, today we'll be discussing about Fermat's little theorem, how it can be applied in solving problems. So let's begin. We'll see many solved examples. Fermat's little theorem says let P be a prime number and let A be an integer that is not a multiple of P. That means P and A are co-prime. Then only we can apply the Fermat's little theorem. P should be a prime number and P and A are co-prime. Then we can write A raised to the power P minus 1 is congruent to 1 modulo P. Or it can be written as A raised to the power P is congruent to A modulo P. Let us take some example, or let us verify first. A is 3, P is 5, so P is a prime number. A and P are co-prime, then we can apply this. Let us verify that this theorem, 3 raised to the power 5, we know that it is 243, and according to this little theorem, it should be 3 raised to the power 5 must be equal to 3 modulo 5. So 3 raised to the power 5 is equal to 243. So if we divide 243 with 5, certainly the remainder is 3. 243 divided by 5 is your remainder is 3. So hence it is verified, and after the verification it is easy to convince. I am not going to prove this theorem because it is not that much needed for our purpose. So the example is 3 raised to the power 6 is congruent to 1 modulo 7. So 7 is a prime number and 3 and 7 are co-prime, so we can apply. So 3 raised to the power 6 we can write 3 raised to the power 6 is congruent to 1 modulo 7. That means when 3 raised to the power 7 is divided, 6 is divided by 7, we get the residue 1. Another example, 13 raised to the power 16 is congruent to 1 modulo 17. 17 is a prime number, 13 and 17 are co-prime. Then we can take this result, 13 raised to the power 16 is congruent to 1 modulo 17. Another example, 9 raised to the power 10 is congruent to 1 modulo 11. 11 is a prime number and 9 and 11 are co-prime. Then we can write 9 raised to the 10 is 1 modulo 11. So Fermat's little theorem is applicable on this condition, and it can be applied to a bigger base. So where this previous knowledge is not applicable or difficult or lengthy, then only we apply this shortcut method. So let us solve some examples or questions. Find the least residue 4 raised to the power 20 modulo 7. So applying this theorem, A raised to the power P minus 1 is equal to 1 modulo P. I can write 4 raised to the power 6 is congruent to 1 modulo 7. 7 is a prime number and 4, 7 are co-prime. So we can write 4 raised to the power 6 is equal to this. Now coming to 20. 20 we have to express in terms of your 6. So 20 can be written as your 6 into multiplies 3 plus 2, 18 plus 2. So 4 to the power 6 is 4 to the power A 4 to the power 20 can be written as 4 raised to the power 26 into 3 into 4 to the power 2. So this gives 1 modulo 7. So this is congruent to 16, 4 raised to the power 16, 16 modulo 7. So 16 divided by 7 gives us your remainder 2. So this is same as 2 modulo 7. So 2 is least residue or the remainder. Next, find the remainder when 3 raised to the power 88,888 is divided by 5. So 5 is P here and this is 3 is A. They are co-prime. So I can write A raised to the power 3 raised to the power 5 minus 1, 4 is congruent to 1 modulo 5. So 3 raised to the power 4, power any number is again your congruent to 1 modulo 5. So 8, 8, 8, 5, 8 is such a big number, but it is divisible by 4. So 4 times of 2, 2, 2, 2, 2. So I can write 3 raised to the power 8, 8, 8, 8 is same as 3 to the power 4 into 2, 2, 2, 2, 2. So this will be congruent to 1 modulo 5. So the remainder is 1. Next, find the remainder when 9 raised to the power 1990 is divided by 11. So 11 is prime number. 9 and 11 are co-prime. So I can write 9 raised to the power 10 is congruent to 1 modulo 11. That means when 9 raised to the 10 is divided by 11, we get the residue 1. So we'll now write 1990 in terms of 10. So this will be 10 into 199. So this is congruent to 1 raised to the power 199 modulo 11. It will be 1 modulo 11. So 1 is a remainder. Find the remainder of 2 raised to the power 1000 when it is divided by 13. So 13 is a prime number. 2 and 13 are co-prime. So we can apply Fermat'S little theorem. So I can write 2 raised to the power 12 is congruent to 1 modulo 13. That means when 2 raised to the 12 is divided by 13, we get the remainder 1. So next is to convert this or to write this 1000 in terms of 12. So 1000 is equal to 12 into 83 plus 4. Divide 1000 with 12. You get 12 8 times 96. 40, 12 3 times 36. We're getting 4. So that means this is your 12 3 times 36 carries 3. 12 8 is our, or this will be 966. 996 plus 4. So I may write 2 raised to the power 1000 is equal to 2 raised to the power 996 into 2 to the power 4. 2 to the power 996 is 2 to the power 12 to the power your 83, thus will be congruent to 1 raised to the power 83 modulo 13. So 2 raised to the power 1000 can be written as 1. Here it will be 16 modulo 13. Because 1 raised to the 83 is again 1. Now 16 modulo 13 means when you will divide 16 with 13, we get remainder is 3. So here the answer is your 3. So remainder is 3. Next, find the remainder when 128 raised to the power 129 is divided by 17. So 17 is a prime number, 128 and 17 are co-prime. So we can apply this theorem. I can write 128 raised to the power 16 p minus 1 is congruent to 1 modulo 17. Now to write 129 in terms of 16, 129 is equal to 16 into 8 plus 1. So 128 to the power 128 into 128 is congruent to 1 raised to the power 128 is again 1. So 128 modulo 17. So when 128 divided by 17, 7 times 109, we get 9 is the remainder. So this is congruent to 9 modulo 17. So 9 is the remainder. So you can practice some more questions so that you can be perfect. So thank you for watching. Subscribe and like the video, comment in the comment section, and keep on watching. Thank you for watching whole video.